Okay, so let's pick up with our talk of inferential statistics, and we're going to talk now about estimation. And what estimation is we're trying to get an estimate of a value that we can't really calculate. So let's say we have a population. So in this case, we got the population of the United States, and we want to calculate a particular thing from them. Let's say their mean heart rate. So we want to get the value of the heart rates from every single person in the United States and then take the average of that. So we want to know what is the mean heart rate. But there's no way you could calculate that because there's over 200 million people here. And so you can't calculate the heart rate of every single person or measure the heart rate of every single person and then take an average. So what do we do instead? We take a sample. We take a random sample of the people. And then this random sample is much smaller in number than this. And so you can measure the heart rate of each one of these people and then calculate the mean. So we talked about before population parameters, and parameters are the values of the population. And for the mean, we talked about before, the mean is represented as mu. So that's a population parameter representing the mean. And this population parameter is something that we can't know. We can't calculate it. But we can get an estimate. And what is our estimate? Well, it's the mean from the sample. So the sample mean is our estimate of the population mean. This one we can calculate, this one we can't. Now we could have just as easily used something else as an estimate of the population mean. Maybe we would use the sample mode or the sample median. You'll remember from the previous videos that these are measures of central tendency. Now, some of these may be better estimators than others. So typically we're going to use the sample mean to estimate the mean of the population. Now there's two different ways we can estimate. There's two different kinds of estimates. There are point estimates and interval estimates. With point estimates, you end up with one single number that is going to represent the number the value that you're trying to estimate, in this case, the mean. Now with interval estimates, you're going to have a range of values that represent this thing we're trying to estimate, the mean. And with that range, you have to specify how confident you think that the thing we're trying to estimate is within that range. So let's look at our example. So initially we said we were trying to measure the average heart rate of everyone in the United States. So we may take our sample and we take the mean of our sample and we come up with one number that is our average. And let's say we came up with the number 74 beats per minute. And that was our point estimate. That's one number that represents this average heart rate of the population, our mu. Now for interval estimates, it works a little differently. Here you specify a range of values. So maybe we say the range is between 68 and 76. And that's our range of values. And we say, well, I'm about 95% sure. I'm 95% sure that mu is somewhere in between here. And so this would be an interval estimate with our range of values specified and our degree of confidence. And so this is going to be the basis of the confidence intervals we're about to go look at. Okay, so let's look at this a different way. So here's our population distribution, right? And so here's how it's distributed. Let's say that it's approximately normally distributed here. We have a mean of this population, which is mu, and we have a standard deviation, which is sigma. This is for heart rate. Now, this is for the population of the United States. So we don't know what these values are. So what do we do then in this case? We take a sample. So we take our random sample, and it's got a distribution like this, and we know that it has a mean that we can calculate, x, which we call x bar, and a standard deviation of s. So these sample statistics we can calculate. Now, if we were to do this little experiment here, this trial, many times, in fact, we do it as many times as possible, then each sample would have its own distribution with its own mean, and they'd each have their own standard deviation. Now we're not going to do this. We're not going to do this many, 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 many times. So these, they're actually unknown as well. But if we did know them, and we took all these sample means and we plotted them onto their own distribution, then we would get our distribution of the sample means. And it would have its mean mu sub x bar and its standard deviation of sigma sub x bar, as we talked about in the previous videos. Now these also, because we're not doing all these many, many trials, which may be an infinite number of trials or just a huge number, because we're not doing these, we're not going to know these either. So there is a lot we don't know and a lot we're going to need to estimate. So let's take a look at our population distribution. So I've redrawn that here, and I've put our mean over here, mu. Now let's say this is normally distributed. So what does that mean? Well, because as we saw in our z-table and normal distribution talks, we know that anything that is about 2 standard deviations away, so let's say this is 1 standard deviation away, 2 standard deviations away here, and this side 1, and then 2. So we got 2 standard deviations here. So we know that anything that falls in this area, that 95% of the things are going to fall within this area. So these are just properties of normal distributions, as we already learned. So something that's 2 standard deviations away from the mean on either side encompasses 95% of all the possible values. And so now let's think of our sample means that we did. So let's say we had our first sample mean, and it fell over here within this area. Then we do another one. So let's say we do a second sample, and so that's here. So our second sample mean also falls within an area. Then we do a third one, a third sample, and that one also falls within the area. Then we do a fourth one, and that one just barely makes it, and that one falls here. And then we do a fifth one, and guess what? The fifth one isn't. The fifth one is outside this area. Then we do a sixth one, and we see that most of these, 95% of the time, it's going to fall within 2 standard deviations away from the population mean. So what the heck does this mean? You're saying, I don't know what mu is anyway, so what does this mean? Well, it means one important thing, that whenever we do one of these, calculate one of these standards, means of the sample means, that we can actually put an interval around this. And if we make that interval the same length here, from here to here, then we can do the same thing. So let's make one here, like that. And then this one will be like that. And I'll do another one over here. And each one of these would have that. And whenever you do one of these sample means, 95% of the time, you're going to get the population mean to be within this interval, right? So any time that you're within this place, whatever the sample mean was within here, that means that the population mean has an interval around it is going to include this, right? Does that make sense? Let me put it a different way. And so what that means is saying that if I say that you are within 5 feet from me, then that's the same thing as saying that I am within 5 feet of you, right? If you're within 5 feet of me, then I'm within 5 feet of you. And so that's kind of what we're saying here, is we're saying that if a sample mean is within 2 standard deviations from the population mean, then that means the same thing as that the population mean is within 2 standard deviations away from the sample mean. And so the times that it's not going to work is when we were not within 2 standard deviations away. Like for this one here, for x5, x bar sub 5, its interval does not include the population mean here. So this time it did not. But if we were to do this 100 times or 1,000,000 times, 95% of the time, we're going to have an interval that does include this population mean. So this is the basis of a confidence interval. We're going to say that 95% of the time, the population mean, the thing that we don't know, is within 2 standard deviations of the thing that we did calculate, which is our standard mean. So another way of saying this is that our confidence interval equals x bar plus or minus 2 times the standard deviation. And so this gives us our confidence interval. So let's go back to our sample. So let's say we took a sample of our people and we got our heart rate mean, our heart rates that we calculated, and we took the mean, and the mean was 76 in our sample. And let's just say for somehow we know what this is, what the standard deviation is. And let's say we know that that is 4. And if someone says, do you know what mu is? And the answer is, of course, no, we don't know, but we do know something. We know the confidence interval, so we know that it is x bar plus or minus 2 times the standard deviation. So we know it's going to be 76 plus 2 times 4, and 76 minus 2 times 4. And so when you do the math, you get 84 and 68. So we'll say that I'm 95% sure that the population mean, that the mean heart rate of the people in the United States is between 68 and 84. That was my confidence interval for mu. So if I was to do this experiment where I took a random sample from the population and took their mean and calculated a confidence interval, let's say I did it 100 times, 95% of the time my interval would contain the population mean. 5% of the time it wouldn't, like in this one here. All right, so that's confidence intervals. We're going to do a little bit more with that, but if you have any questions, please put a comment below or email me and let me know. All right, thank you.